Tardes. Gracias por continuar en las pláticas de la conferencia OPUMA. Entonces, para continuar con las pláticas del día de hoy, ahorita tenemos la presentación del doctor Sergio León Zaval, que se encuentra ubicado en la Universidad de Sydney. Y bueno, nos va a presentar su plática, que es Astrophotonics, when Astronomy meets Photonics. El doctor Sergio León Zaval obtuvo su doctorado en la Universidad de Bath, en el Reino Unido, en el 2006. Actualmente es profesor asociado en la Facultad de Física en la Universidad de Sydney y es también el director del Sydney Astrophotonics Instrumentations Laboratory, SAIL, así como el director del Instituto de Fotónica y Ciencias Ópticas, IPOS. Entonces, rápidamente una semblanza. Esto es lo mismo, ¿no? Bueno, también el profesor, el doctor León Zaval, ha estado trabajando tiene más de 16 años de experiencia en el campo de investigación de la fotónica. Él hizo una gran contribución en el campo de las fibras ópticas. También en aplicaciones de astrofotónica e instrumentación óptica. También él es un Optica Fellow y miembro del Consejo Australiano y de Nueva Zelanda de la Sociedad de Óptica. En 2019 se le dio el premio John Love Award, ANSOS, y también es reconocido por múltiples descubrimientos y contribuciones tecnológicas en el campo de la óptica y fotónica. Entonces, bueno, tenemos el placer de que nos presente su plática. Sergio, por favor, te cedo la palabra.
Muchas gracias, Amado. Lo primero es daros las gracias por darme esta oportunidad. La verdad que me da mucha pena porque en principio íbamos a intentar que estuviera allí presente, pero al final me salió algo que no pude quitar de la agenda y no ha podido ser. Pero espero que la próxima visita que haga a México me pueda pasar por allí. Gracias, Amado, por la invitación, Eloy por el seguimiento. Y la otra cosa que quiero decir es disculparos porque la charla la voy a dar en inglés. Soy de Sevilla, originalmente de España, pero llevo 22 años fuera y la verdad que mi carrera incluso mi grado lo hice en inglés, por lo cual dar la charla en español me llevaría bastante tiempo porque los términos se me van un poco ya de la cabeza. Bueno, pues lo que voy a hacer es empezar a compartir. Estupendo. Yo creo que ahora sí podéis ver la presentación. Pues nada, lo primero lo que voy a hablar hoy es del tema de astrofotónica, pero lo dicho, no es un full review, pero es un poco como las áreas en las que yo creo que está influyendo más el tema en astronomía. Y lo que quería dejar aquí para quedar claro que no es un full review, algunos de los reviews y nuevos papers que han salido durante los últimos años. Por si alguien más quiere leer un poco más y quiere saber un poco más del tema de astrofotónica. De acuerdo. So the first thing that I want to actually mention is that you look at the size of the telescopes in the last few years. You can see that it's what is called the rise of the massive telescopes. Okay, and astronomers are not very inventive when they're giving names to telescopes. This one is actually the ELT, which stands for Extremely Large Telescope. They didn't think much about the name, and you can tell by that. But I want to give you that sense of size that we're talking here, right? So you look at this picture of the Opera House in Sydney, and this is actually the artist's impression of the ELT when it will be actually built. So basically, it's around 798 segments of 1.5 meters across, and it weighs around 245 kilos each piece each component. So we're talking about a telescope that is 40 meters across, and it's actually 260 tons in weight. Okay. Now, you think about that. This is interesting, but the size of the photons still remain the same, right? So if we're looking about the scaling the current astronomical instruments, it will be extremely costly because most of the instruments, especially in the spectroscopy domain, depends on the actual aperture size of the telescope. So you need to scale things accordingly. Now, that's why we think that that is a new approach that is needed, and that's the use of photonics. That's what I'm trying to actually to convey to you today, to see if I can convince you that astrophotonics is the right way to go for the future astronomical ventures. So the first thing I want to talk, to give you the intro about how photonics is important in astronomy, is the following. Okay, when we're talking about the multi-mode, few mode, and single mode regime in optical waveguides, we normally talking about, for example, in the optical fibers, we're talking about multi-mode fibers, which is larger core. We're talking about single mode fibers with a smaller core that only guides one mode. It's normally the fundamental mode. So how that analogy comes into play when you're talking about astronomy? So that is one thing in astronomy that is actually what is called the seeing. It's actually how good is your point and spread function at the focal plane of the telescope. Okay, how your spot, your focus spot is for your science. Will be for coupling into instrument, for imaging, for etc. etc. So that's what is called the diffraction limited regime, right? So, and this is what is called seeing limited. So we see a case here that the seeing is actually affected by the turbulence and the atmosphere, and how much that phase of the wavefront gets aberrated with that perturbations. So we're talking about a small telescope. In this case, T is the aperture of the telescope, and R0 is a measure of how bad or how good is the turbulence of the in front on your field of view of the telescope. So if we have a telescope that is in size comparable to the actual R0 number, which is normally in centimeters, you can tell that you can have an instrument that is diffraction limited. As an instrument like that, you will have a nice 80 pattern ring for your PSF, and everything will work beautifully, and you could probably couple into single mode waveguides, etc., etc. Now, however, when the R0 gets worse, which is normally the case, your seeing is starting to change now, and then you get into a bit more aberrated, and that's normally the case when your aperture telescope is much larger than the R0 of your seeing in your observatory. Okay. Now, if you look at that, and we're looking in the quasi-diffraction limited regime, you could say that you will be able to use instruments of photonics or optics that will be working in the lower few mode regime, right? It will go here the LP modes of circular symmetric waveguides. This is actually the LP approximation of the modes. So you could represent those PSF with a combination of those, for example, like a base, modal base. However, when you go to the worst seeing, what is happening there is that your focal plane becomes highly multimoded, right? And in that case, when we need to talk about all the high order modes that will be that we're familiar with in the photonics regime. Now, what happened? Astronomy needs light because they're faint objects. So we mean that we need buckets, light bucket, and that normally the use of highly multimode fibers have been the norm in astronomy for the last few years, right? However, we know here, and this is a forum that I don't need to explain this too much, that photonics functions are governed and limited by modal content of the light. Okay, so if we want to apply particular functions, particular new functionalities to the light, to extract the science for astronomy in the photonics regime, we need to actually be able to control or to know the modal content of the light coming from the telescope. Now, what I like to call is what I call the photonics enablers in astronomy. The first one that have been around for many years, for 30 plus years, is what is called adaptive optics. In that one, what you have is basically a system, a very complex system in a sense, in which you have your telescope, the light gets aberrated by the atmospheric turbulence, and then it distorts your wavefront, right? And then what you have is the forward mirror, and then you have what is called a wavefront sensor. So in there, what you can do is that you can actually sense the wavefront, have a close look with the mirror, and correct for that aberration on the sky. And basically, this is an example of it. This is an on and off AO system, in which you can see that you can recover quite nicely a quasi-diffraction limited limited area pattern there. Now, the other one that we like as photonic enabler is what we call the photonic lantern. And this is something that I know that Mato have been working for many years, and probably some of you are very familiar with it. But this is a photonics device that can convert light from a multi-mode system, a waveguide multi-mode system, to a single mode or few mode system, and vice versa. And this will a low lost manner. So a photonic lantern, what I would like to call is, I would like to actually mention that photonic lanterns are any system that transforms a modal system to another one, okay? Conserving the light, the entropy, and the energy. So basically what we have is that you can have from single mode to multi-mode, single mode to few mode, multi-mode, etc., and etc. So how does that actually work? By the second law of thermodynamics, you cannot actually have an arbitrarily excited set of multi-modes coupled into a single mode system, into one single mode system. And the reason for that is because you will change the entropy of the system, correct? So basically, you cannot do that because physics does not allow you to do that. However, what you can do is to actually transform a set of different modes into an array, a set of fundamental modes, but with the same number of degrees of freedom. So what it means that you conserve the number of modes with the same number of fundamental modes, you will be able to create a low-lost entropy system. And that's basically here. So how we actually do that in practice, we have fabricated them in three different ways. One of them is by using the multi-core fibers, and the other one by using bundles of fibers, single-mode fibers. And also we have used what is called laser-written waveguides. So that's basically a high-power laser that can write waveguides within a glass bulk platform. So normally what you do is that you create a composite waveguide. What you have is in your multi-core fiber, for example, here, you will put a jacket around it with a lower refractive index in such a way that when you actually create that composite waveguide by physically fusing together and creating that transition from the multi-mode end to the single mode array, you can conserve those degrees of freedom, you can conserve the entropy with what we call an adiabatic transition, okay? And in this case, adiabatic is not in the sense of thermodynamics. Adiabatic is that is gradual enough for the overlap interval of the modes to be actually as good as possible at each point of the transition when the whole waveguide is being reduced in size. So that's basically in a nutshell how it is. There is a picture of one device here that goes from 7 single mode fibers to a few mode fiber containing 7 scalar modes, and this is actually a picture of the real device. So that's how we do. That's how they look. Nowadays we can actually package them in a way that they will be completely agnostic to the device inside. In this case, the actual transition is here, packaged at the fiber connector, the same here and there. And then you can just have different pigtails. So basically it will look like any other device you can buy from Thought Labs. Now, once I introduce those two photonic enablers that we normally use for astrophotonics, most of the use that we are doing in astrophotonics nowadays can actually use the lanterns, so can use adaptive optics in front of the instrument if you wish. So the thing that started a little bit everything in astrophotonics was what we call the photonics spectral filtering. And let me explain why that is important in astronomy. So when you look at the sky, especially at night, what we call the OH background is the hydroxyl elements emitting lines in the near infrared. This is actually a plot of how many of those lines are actually out there from 1 micron to 2.5 microns in the near infrared. And this is a video of how much variation is in that. So you look at the night and you see that it's dark. If our eyes were able to capture the light in the near infrared, it would be 10 times brighter than daylight. Okay? And that's a big nonsense for astronomers. Basically, what they need to do is to look at beyond that forest of lines and try to look for those faint objects, distant galaxies, etc., etc. So in this case, what we focus for our work within 2 different bands, how they call them in astronomy. different to photonics and telecom, of course. And it's the J band and the H band, so which is 1.5, 1 micron to 1.8 micron in the near infrared or so. Now, what the concept that we came with and sort of sparked a little bit of area of astrophotonics many years ago is what is called the OH background filtering unit. So we thought, okay, we can actually describe and to design fiber gratings to block those lines very accurately and very with high signal to noise, and then get rid of that background for astronomers to get a clean sky, clean faint objects into the spectrograph. Okay, so this was the concept, but in order to do that, and you know that well, to write fiber gratings into multimode fibers is something that is extremely difficult, and you will not get a clear signal and clear fidelity of those lines that you need. So what we decided is to create this concept, is to have photonic lanterns that will divide the large light bucket collecting ability on the telescope into single mode waveguides, and then each one of those will have a OH suppression fiber grating, and then you can combine that back into a normal standard astronomical multimode spectrograph. And this was actually the concept that we came with. So, and that's actually what we managed to do. So after several years of the research and development, we created the first instrument that is called Gnosis, and a follow-up instrument that is called Praxis. And in this one, what we have is 266 OH lines being knocked and suppressed with targeted fiber gradient lines and notch responses here. So this is a picture of the instrument itself. So they have two lanterns here, two 19-to-1 lanterns here, and they have two different bands of FPG gradients spliced between them. And that was installed into the AET, which is a telescope in Australia. It's a 4-meter telescope in the middle of Australia. So this is some of the results that we have here. But before I go to that, I'll show you here on the right. This is the spectra that you will get normally from the sky. So those are the lines that you don't want to see because it's just artifacts from the atmosphere. And then those are the gratings in yellow and blue that we design to knock all those lines one by one. And there are 133 OH lines in two single grating designs. So, and this is basically the output once that you have filtered those lines from 1.4 to 1.7. And this is the first results that we have here. And we see this is actually the one on top is the control spectra. And then the one on yellow is the actual raw response. And then we got the calibrated in blue here. And you see, okay, there is nothing here. This is just blank. Fantastic. You managed to block all the light. You could put a brick in the middle, right? But if you look at carefully here, what they got them very excited that you could see what is called the iron 2 line, which actually is a strong signature for a distant galaxy with extremely high redshift. And this was actually the first time ever that this could be seen at this range in a spectrograph of these properties. So that was a huge success, and we are now working in the second generation with different telescopes. Now, that actually span a different area of research in different platforms. One of them is actually using the fiber gratings, but by line scanning, and this is a collaboration with Jena University and Macquarie University, in which they can actually do a periodic fiber gratings by scanning the light of the core, instead to have the complex system that we introduced for interferometer that we introduced to write the periodic gratings. So this is actually ongoing work, and from our colleagues in Germany. The other platform that is used is actually ULI for this OH sky suppression. So basically what they can do in a block of glass, they can write everything. They can write from the photonic lantern, multimode waveguide to single mode waveguides, to the gratings themselves. Okay, and they can do that in a single piece of glass by using the laser written waveguides platform. So this is a first demonstration that was published many years ago. However, this suffers a little bit for the overall losses of the system, and also how large number of waveguides you can implement into that. So this is actually a work in progress and something that is quite promising, but is still not being fully demonstrated. The other area that we work with the University of Maryland is to replicate that into planar waveguides. How you will do that? The way that you actually manage to create those fiber gratings, so that grating response is by just simply changing the properties of the waveguides along the propagation. Like that, you can create that effective index change that will give you an effective response in the frequency, like a Fabry grating does by inducing the change of refractive index in the core. So this is actually extremely encouraging because it's a passive platform like that. It can be designed very precisely, and it's producing significant, very good results. For example, here you can see a large multi-notch platform that was designed on chip with a structure like this. So this is work in progress and quite exciting because it will manage to reduce the whole footprint of the actual devices and instruments themselves. Now that's one. The second one, in which we believe astronomy and will make a big impact, especially photonics in this case, is for the spectroscopy. Okay, and let me give you a little bit of background why this is important in astronomy. And I'm sure that you heard talks about astronomy already on the conference. So basically, spectroscopy is one of the most used and powerful techniques in astronomy, and basically because each component, each element, will have a particular emission and absorption properties. And those are like fingerprints, right? And those are the ones that are used for most of the science that they actually do. The other important one is one that is quite popular in recent years, which is actually the exoplanet. They're looking for the next second Earth, okay? And for that, what they use is a high-resolution spectroscopy system that is called the Doppler method, or the radial velocity method. In that one, what you need to have is a extremely high resolving powered spectrograph that is extremely stable over years, right? So that's actually one of the challenges that they have in the spectroscopy. Now, what is the diffraction limited spectrograph dilemma? Okay, if you're familiar with how you do a spectroscopy, you normally, the ones that you buy off the shelf, and you can buy from Ocean Optics, many different ones, they normally give you a particular resolution, right, for your spectra. And that is governed by the entrance slit of your spectrograph most of the time, okay? So how normally works is that those two, the resolution and the entrance slit of the spectrograph, what is going to be dispersed into the sensor, is actually a link that cannot be actually changed, right? So when you get a spectrograph on the shelf and you increase the resolution, the only thing that they do, it is a fiber-fed spectrograph, is that they put a mask in front in which the slit is actually wider or narrower, right? So, and that's how you increase the resolution. However, there's a problem there. That means that you throw away a lot of the light. Now, the solution that we thought with Astrophotonics was, okay, let's try to remap that multi-mode entrance of the spectrograph, and instead to put a slit and throw away the light, let's try to change the morphology in which we can actually change from a fat entry slit to a thin diffraction limited or quasi diffraction limited slit. And that's basically what the photonic lantern can do for you. Okay, this is a picture. So what you have here is a multi-mode, few mode indivisible, and then you can actually, with a photonic lantern, you can slice that light into the single mode waveguides, and then you can disperse that and have a very compact instrument, because quasi diffraction limited light is very easy to disperse, is behaved very well, and you can have very compact optics to do so. So this is actually how it works. This is what we call the multi-core photonic tiger. This is actually a lantern that is made with a multi-core fiber. So this is what we have, a lantern with 19 cores, and then we have the lantern made from the multi-core. And this is a real image. This is actually the multi-mode part of the lantern, which is around 30 microns or so in diameter. And this is a real near-field image of that waveguide indivisible, which when you go through the lantern conversion, what you have is that you separate them into the single-mode waveguides. Hence, now you can actually use a very simple system to disperse the light and create your spectrograph in a compact manner, in a very efficient way, simply by using the multi-core array and doing some mechanical rotation. You can actually disperse and get all the information for each one of the cores that then you combine together to give you the spectra. And that's basically what we did. So just to demonstrate the concept, we did a very simple, cheap 3D printed prototype, the first one. Now we have more complex and more elaborated instruments. But this actually shows the principle very well. We can have extremely high resolution spectrograph. So in the bottom here, where you get the blue one, is the high trend. So that's actually coming from extremely high resolution data over the years. And the one on the top are the different bands of our spectrograph. And we can actually reproduce, this is raw data, so it's not normalized or calibrated. That's why you got the bands. But you can actually get every single line at the same resolution that high resolution spectrograph. And just to show you something here, this is the raw data on the sensor. And you can see that each one of those lines is one core dispersed in the spectral domain. And then here you can see all the cores in blank. Why? Because that's at H alpha, so alpha emission line from one of the stars that we're looking at. And you can see how you can see somehow imprinted, inheriting where the cores actually are on the spectra. So this is what we think that is going to do, and it's already making a difference in we're designing a couple of instruments for different telescopes to do high precision RV velocities for the astronomy with this technology. Now, but we can go further and we can go what we call the fully photonics. And then in that sense, what we do is actually now, instead to use a bulk spectrograph, like we just showed you now, we can actually combine the photonic capability of dividing the light into single mode with the photonic capability of dispersing and getting spectral information in a photonic chip platform. So basically, this is the concept, that's what we call the photonic chip. Basically, it's to build a spectrograph within a photonics platform. And it's something like that. You got the photonic lantern, you splice that to a spectrograph, and in this case, is a AWG, which I'll explain in a second. And then you imprint that into the sensor that gives you the dispersed response of the wavelength. And this is actually how it works. What we use, we noticed from telecom that will be very useful, is array waveguide gratings. And basically, this is what it is. It's just simple waveguides that each one of those got a slightly longer length than the others. So it's giving you a differential phase delay. And that differential phase delay, when you go to the actual focal surface here, what it's creating is an interference pattern that guides somehow the light to different points at the output, which is basically a spectrograph. So it behaves in a sense like a dispersive element, like a bulk grating will do. And that's basically the concept. And this is actually what we get. So what we did a proof of concept. We built one of those in-house. We took it to the telescope again, to the Cosmograph 4-meter telescope. And then we tested into one of the brightest star in the sky, which is Antares. And this is basically what you get. This is a raw spectra of Antares. So we have here is wavelength order, and we have the different fibers outputs for the lantern being dispersed from the AWGs. So that was extremely exciting. But as you can see here, the size of that spectrograph is actually half size of the palm of your hand, which is actually quite impressive for the capabilities that we can get in resolution and efficiency there. So this is work that is in progress. I'm just going to give you a little bit of a hint of the current efforts pushing this at the moment. And we have a collaboration with the University of Maryland. They're very good in fabricating silicon nitride waveguides. And they have different platforms that are trying different geometries to improve the efficiency, to improve the performance, to increase the resolution, etc., etc. So the results are very encouraging. We're actually producing devices with extremely high throughput and with very good dispersion properties with high resolution. And this, as I say, stay tuned because this is actually work in progress. There is another paper coming soon in the next few months. The other group that is pushing this quite strongly is in Caltech. Is my colleague named Jovanovic, and they are actually working with the Lingetech and Bright Photonics, and they are building what they call a two-stage device. In this one, what they're thinking is they create the first device which got a coarse resolution, and then that one gets fed into a second device which a much larger resolution. Basically, as you do in gratings, that the resolution is given by the number of lines of the grating. Here, your resolution is pretty much governed by the number of waveguides and the length of the waveguide phase difference, right? So you can see here, this is the low order, low resolution, and this much larger device, it will be the high order, high resolution. So when you combine both of them, they can get an extremely impressive over the 10,000 resolution which is 0.001 nanometers in the near infrared, and it's extremely compact. It's only by 8 by 3 millimeters in size. These are some of the pictures that you can see of the dispersed spectra at the output of those focal surface at the output of the device. Now that's the other part. The other area in which we have done a lot of work in astrophotonics, and actually an area that will probably have some impact in the near future, is in calibration. Okay, so basically, I'm sure that many of you are aware of what calibration systems are there for astronomy, especially with the laser frequency comb, etc., which I will mention briefly. But the major driver in astronomy for high resolution and stable calibration sources comes from what I mentioned before, for the exoplanet community. So to be able to detect that Doppler spectroscopy. And the Doppler spectroscopy is a very simple concept, but very difficult to measure. What it is that when you have a star and a planet, and they're rotating with each other from Earth, what we can do is that we can see that Doppler effect. What it will do is that when the star and the planets are rotating in one direction or another, you will have a red or you will have a blue shift on that emission or assertion lines of the target that you're looking at. Okay. However, that change in wavelength is extremely small. I mean, we're talking about a fractional velocity shift of 1/300,000. So we're talking about they called 1 meter a second is around 0.00005 nanometers. So we're talking, you need a calibration for a spectrograph that can sense at a 0.00005 nanometers shift in your peak. So that's extremely difficult. Like what I say sometimes, like seeing from Sydney to Melbourne, that is around 1,200 kilometers, to see a baby crawling against you from that distance in a Doppler effect. Okay, so that's actually extremely factor. So the way that you do that is to have very stable calibration sources, and one of the most well-known one is what they call the mode-lock laser combs, and the electro-optic frequency combs. Right, this is the famous ones. They gave the Nobel Prize and etc. for frequency combs several years ago, and they're basically based in nonlinearities and in the temporal in the Fourier transform limited response of mode-lock lasers and frequency doubling OPAs, etc. Now, these are the most standard ones that people are using, and they're more reliable. However, the new and coming platforms like soliton microcombs, they behave in the nonlinear regime. So basically, you have Kerr nonlinearity creating combs, and then you can actually tailor in time and frequency. And then there's also the standard Fabry-Perot etalon, but in different ways that the standard etalon cavity that you have in mind with two pieces of glass or air in the middle. Now there have been more clever ways to do Fabry-Perot etalons in a photonic way, and that's the one that I'm going to mention now briefly. Is what we call the photonic comb calibrator. So in this one, what we have is that we create an etalon within an optical fiber cavity, which is around 400 microns in length, and it got the actual core size is around 4 microns in diameter. So what you do is that you create thin film mirrors within that fiber core, and give you a exquisite Fabry-Perot etalon cavity. And this is actually real data from the supercontinuum, in which you help all the lines from 400 to 800 nanometers. So what you can do now is to laser lock that cavity by the thermal control to a rubidium absorption spectroscopy, which is called laser locking, right? That they use in the quantum, and some of you probably very aware with. And you can create an extremely compact system that gives you up to around 0.1 meters a second stability. So, and that's actually thanks to have that photonic concept of the fiber Fabry-Perot etalon cavity and laser locking platforms. No, we took that and we use that also for calibrating effectively the image of the sensor. And how we do that? What we do is that we can actually, in a single snapshot, we went to the AAT, which is the telescope here. And what you can see here is what is called the 2DF. This is actually a positioner of fiber, robotic positioner that can position up to 400 80 fibers within the focal plane. This is for multi-object galaxy observation. And this pattern that you have here is all those input fibers being illuminated with our Etalon cavity with another telescope. So basically we have a baby telescope coupling into a huge, big telescope to be able to calibrate the spectra, which is called Hermes. This is the spectra that we have, and this picture here doesn't make justice of the size. This is in a table that is around 4 by 8 meters length. And we're talking about optics of the size of twice my head, basically. And what we did was to use our small shoebox calibrator. We took it there, and we managed to imprint a lot of little spots in the sensor, and like that, calibrated in wavelength and calibrated in image, because you can also correct the optical aberrations on the system by looking how the spot is actually aberrated or deformed. So, and that came from this nice paper in which we managed to reconstruct all that information and to recover a lot of spectral resolution. That's a spectrogram for the science that they do for the galaxy formation. Now, the one before last part that I want to talk about is astrophotonics in imaging and interferometry. And this one is a particularly interesting one because it used extremely interesting concepts in photonics, in coupling, and optical waveguides. So we're talking about imaging and interferometry in astronomy. What you normally do is that what you have is a concept of multi-aperture, right? So basically what you can have is you have several telescopes looking at the same object, or you can have the same telescope that which aperture is divided in different segments, right? And then you do the interferometry, the spatial interferometry between those particular points. So the important thing here that what we care about is about the spatial incoherence that we have due to the astrophysical source, okay? But not the atmosphere. And that's the beauty about interferometry in astronomy, that you can actually forget about what the atmosphere is doing to your waveform, because that gets calibrated or normalized somehow when you're doing the interferometry. So that's why this is a very strong, important area in astronomy nowadays. So the major areas of research in astrophotonics in this area are with pupil remappers for single telescope interferometry, beam combiners, and nulling interferometry. Those are the three ones that I would like to put. Now, this is a concept here that it was developed for a couple of my colleagues here at Sydney Uni. And this is actually the vision that they have for integrated optics and photonics in astronomy. So what you have is that you can have a telescope pupil, and then that is segmenting. Then you have ULI waveguides that create some function, interferometry. Then you can inject light into a chip in which you can control phases to give you the nulling properties and interferometry properties. And then after that, you can use that another integrated photonics to create the dispersion and get the wavelength diversity, wavelength information that you need on this area too. So this is a full concept that we are working towards in the next few years. Now, to be more precise, basically what we're trying to explore now in astrophotonics is to use simple concepts in photonics, like couplers, phase shifters, waveguide remappers, etc., in order to use that functionality within the context of astronomy. Now, and the way that we do that is by being clever about how we incorporate them to be able to measure the coherent coefficient and the split of light in the different components. Okay, so let me just I'm going to give you a couple of examples now how we use that. But in here, for example, there is a concept for the BLT in which you have the different telescope looking at the same source, and then you have delay lines to do the interferometry, and then you can have the beam combiner, you can have wild light fringes, disperse image, and you can apply all those simple photonic concepts to extract phase information on the source that you're looking at, which is an important bit at the end of the day. Now, I'm going to tell you something that not many people is aware of. Is the concept of gravity. I don't know how many of you heard about gravity, the instrument at the BLT, and this is actually a beam combiner. So it's actually what is called an ABCD combiner for long-base interferometry. So you have these four 8.2 meters telescope that they are combined through very long tubes or light, and they go to the instrument here. So this is basically gravity instrument. It's not extremely big, right? It's like a half size of a car. But for me, what is exciting is actually what is in this little aluminum foil wrap thing, which is the heart of gravity. Okay, and in the heart of gravity, what you have is somehow simple but very elegant photonic concept of the ABCD combiner. So it's basically this is a chip that's inside gravity, and what you have is it's four different waveguides from the four telescopes that are combined in a pairwise scheme. And then by association of splitters and X couplers and phase shifter, what you got is at the output, you get a very informed intensity map of how the phase between the four telescopes is actually happening. So what is coherent, what is not coherent, and what information you have from whatever source you are looking at with the four 8-meter telescopes. Now, I'm not going to go into the details, but just to tell you again, I'm not sure how many people is aware of this in photonics, but this gravity instrument have produced some of the most spectacular results in astronomy in the last few years. And in fact, it's said that it was the first successful test of Einstein general relativity when they managed to measure some information near a supermassive black hole. And furthermore, I'll say that this gravity corroboration of this was actually one of the key factors for the Nobel Prize that happened a couple of years ago. So this actually has been an impressive photonics instrument that had changed some of the astronomy concepts that we know today. Now, other thing that you can do now, instead to use 4 different telescopes, is to use a large telescope, and you can use different segments, different parts of the telescope to do interferometry. Okay. So in this case, what we call a pupil remapper. So what you will have is your telescope, you have your focal plane, you have your pupil plane, and now you can use the formal mirror, for example, to be able to segment that pupil plane into different sections. And you can do interferometry between those different sections of the telescope pupil plane. So the pupil remapper, what it can do is that you can actually target some of those areas to create different baselines on your same single aperture. And then by using a ULI device, you can create the waveguides here, and you do the coupling, and you do the couplers, waveguide couplers, and you do the ABCD combiner, and you can disperse that and get the wavelength diversity. So basically, you can do the same thing that you saw in gravity, but you can do with on-chip ULI and with one single telescope aperture. And this is basically what it was done. This some of the optical setup that went to the telescope. So basically, what we have is these are different waveguides on the segments that were actually different baselines for the interferometry. And this is a picture with red light just for the dramatic purposes. Obviously, this is in the near infrared, but just to see how the waveguides look like into the system. And what we have is this. Basically, what we can do is that we can actually get by the phase diversity and wavelength diversity information of the spatial frequency Fourier, we can extrapolate a lot of information from the target and the source, like the radial of the sources, like the different phase components between the star and companion planets. So this is exciting because it allows one single telescope to do very advanced interferometry. Now, the last area on interferometry I want to talk about is what is called nulling interferometry. Okay, this started with a very simple concept, and the concept was actually based. It was done in the Palomar Observatory, and it was based on a single concept of having one single mode fiber at the focal plane, and having two telescopes to focus into the same single mode core fiber. Okay. Just by doing that, you create a simple interferometer, and that simple interferometer will be able to actually what is called the projection on the sky. So the idea of a nulling interferometry is that it gives you ups and downs on nulls, right? That you will do in a 2 points interferometer, but you can project that into the sky. What it means that you have a star a bright star, and you have a companion planet that is rotating around, if you create your nuller in the photonic device that can map especially on the sky, that means that there are areas, and this is a video here, I don't know you can see well or not. I don't know how far are you from the let me get that. Oh, sorry. That video there, what it's telling you is that when you have the planet in the middle, you can null the planet in the dark fringe, and the star, in the null fringe, and then you can have the planet going around, and at some point you can actually have a very good visibility between the planet and the star. So what it's doing is that by using an interference pattern on a sky, projected on a sky, on the Fourier domain, you can actually now block the bright star to see and observe the planet around it. Okay, and that's what the concept of the Palomar fiber nuller was many years ago. Now we have moved from that to be a bit more elegant, let's say, on the device, and we use what we call the glint nuller. So what we do is that again we use the same pupil remapper technique, so single aperture telescope, segmentation, and then we use different parts of the telescope to create the baselines. And we couple that into a ULI device, which is just a simple device like this. So basically what you have is 2 waveguides, and then those 2 are actually called wire splitters, and then you got directional couplers and give you a response and intensity and of the coupling conditions. So this is actually very stable, and we built this instrument. It's a small instrument. It's just like 3 times the size of a shoebox, and we took that to the Subaru telescope in Mauna Kea in Hawaii, and that's actually installed there at the moment, and it's doing amazing science. This is actually some of the pictures from the students, very happy students that managed to get a trip to Hawaii, and this is the box that is actually attached at the instrument area of the telescope. This is Tiffany, which is actually doing the commissioning of the instrument, and he was extremely excited because for the first time there, we managed to measure with this very compact instrument that is not much larger than that box that you see there. We managed to measure the stellar diameter of a target, which is alpha tau. It's a typical target in astronomy for calibration. We managed to measure the stellar diameter at 17.2 mass, which you will say, okay, fantastic, well done. But the important factor here is that the actual diffraction limit of the telescope itself is 40 mass. What it means that actually with this little add-on to the telescope, we managed to improve the resolving power, the resolution of the telescope by a factor of +2. Right? So just by adding that. So that was actually very exciting to see, and this is actually work in progress. We got funding for the 2nd generation that will have not 2 waveguides, but will have 8 waveguides input, and will increase the resolution and the diversity by quite significantly. So that is there. The last bit that I want to talk about, and I think we're doing well with time, and it will be just 3 or 4 minutes. So it's actually about all photonics wavefront sensing, and this is perhaps one of the areas that have been had more interest in the last year or 2 years. And I'm going to give you just a flavor of what it is, but I will not go into the details because we're running out of time. So basically, when you're talking about wavefront sensing in fiber with fiber modes, if we look at about what wavefront aberrations are, they're normally defined by the modal basis, right? And one of the standard ones in optics that we are not here in this crowd is what is called the Zernike polynomials, right? This is just an orthogonal Zernike base modes to define aberrations from a stigma, comma, whatever, how you call it. You can use Zernike modes to do that. Now, if you look at about the Lagarde-Gaussian modes or the LP-odd even approximation in optical fibers, and even though there are different planes, but again, the principal states, they also operate in a 2D basis in polar coordinates, which got extremely similar geometry and symmetry, right? And when you look at them side to side, then you start thinking, okay, so if I'm able to detect in my system the number of the type, intensity, and phases of the LP modes into my multimode fiber, I will be able to have a direct correlation of what is the Zernike component of the modes at that input focal plane of my multimode waveguide. Okay, and that's basically the concept that sparked this idea. So how we actually do that What we thought, okay, let's use a photonic lantern, because a photonic lantern is a device that gives you a mechanical, automechanical optical transformation that is fixed, the transfer matrix, from a multimode system to a single mode waveguide system, different intensities and phases. So what we can say is that if we can measure from the output what is the modal component here on the waveguide in LP component, then we can infer what at that focal plane the Czernicki aberrations were, right? So, and that's basically what we try to do. So we model this just to be sure that we're not actually dreaming about, thinking about something that was wrong. And we clearly noticed that, interestingly, it was working quite nicely, but also was able to sense certain aberrations that they are not easy or even possible to sense in some of the common wavefront sensors in the focal plane nowadays. For example, the focus and astigmatism in the pupil plane, they look very similar, and the image intensity is also extremely similar. So some of the current wavefront sensors cannot distinguish in which is the sign for the focus of astigmatism. However, if you look at here, this is a representation of the intensity output of the 19 cores, depending on the input conditions. So basically, we input at focus of -2 and +2 at the lantern, and then we measure in intensity what is coming in the multi-core fiber. And we can see that there is an extreme difference between them here. So that means that the photonic lantern will be able to actually distinguish between those apparently indistinguishable modes with current technologies. And that's what will spark the whole interest to start working on this. Now, how we measure that? We created a simple setup. So we say, okay, we have our photonic lantern here at the focal plane, like it will be at the focal plane of the telescope. And we use a standard SLM setup to create the Czernickis, to create the aberration into the focal plane. And what we do is that we can measure the output intensity of all the cores depending on what is the image plane that we input at the front of the photonic lantern in the multimode. Okay, so that's the picture of the lantern that we use. And the trick here is that we want to infer what is the complex amplitude, what is actually the composition of the modes at the input of the photonic lantern, the multimode N, by only measuring the intensities of the outputs. So it means that we don't have all the information because the transfer metric will be quite clear. You have the intensity and phase of all the modes in the multimode area. Your transfer metric will tell you what is the intensity and phase of all the single mode cores, right? However, what we want to do is to measure all the intensity without having to measure the phase of all the cores, because that will be an interferometry nightmare. You will need to do like a 2n minus n to the square different pairwise combination to be able to infer the phase on all those single mode fibers. Now, that's basically the idea. What we have is that we produce the atmosphere, we record the intensity, and then we can infer what is the Czernicki component of the focal plane at that particular point. Now, how we do that with measuring the phase of the single mode inputs? We applied a neural network. We applied a machine learning mechanism. So what we say is that the transfer matrix will be able to give us the fluxes at the output and the phases. However, without knowing the phases, we still can infer the input. And that's how we did it, okay? What we did is actually, we say, we generate a waveform by drawing the quasi-random distribution of Czernicki coefficients for the first 10 modes in this particular case. And then we acquired 60,000 measurements, right? Now, from that, it took around 30 seconds in a current system that doesn't take that long. We kept 20% secret, and we used 80% to train our network. Basically, we create a neural network that tells us we have these Czernicki combinations, and this is the output in intensity only that we have in the single mode. So what we did was that, and then with that 20%, we tested how well we could predict the wavefront, and that's basically what we did, and we published 2-3 years ago. And we could reproduce, actually, basically, the aberrations of the focal plane only by measuring 19 intensities with RMS error of 5 to 10 to the minus 3 pi radians. That's actually extremely impressive for a simple device like that. And this is some of the residuals that we actually got. Not only that, we noticed that even by changing the number of samples, we still got a very good agreement for different, from tilt, astigmatism, focus, etc., all the different Czernicki aberrations, even with a lower number of samples compared to the higher numbers. So that was actually quite encouraging, and it's a lot of work that's been going on since then. So, but to finish, what I would like to show is this. We took it then to the Subaru telescope. We put it into looking at the star Berta Virginis, and this is what you see on the telescope. So basically, what you see is what my student, when we saw it, say, "Oh, brilliant! We got the Christmas tree working." Basically, what we have is a lot of flickering lights from the cores, because their flickering is inferring how that wavefront is changing in real time, as you saw here in the spots. So let me just get that again. So when that change, the PSF change after the sketch say, "Oh, that hypothetic system," that's the response on the single mode course you get. So what is the Holy Grail? And I'm going to finish with this. The Holy Grail that we're working at the moment is what we call the hybrid concept. And in that concept, what we want to do is create a photonic lantern in which it's not made by standard core sizes, but one of them is slightly different. And that slightly different core, what it can do is that I can actually manage to capture most of the light in the fundamental mode and the lower order modes into the input focal plane. So like that, what we do is that we can take that single mode waveguide to the science for the spectrograph, and then we can use the remaining 18 waveguides to do the wavefront sense and control in a closed loop. And we're currently working on that on the telescope, and it's working, so stay tuned because it probably will be published in the next few months. So, and I think that with this, I'm going to finish, and without also putting here a bit of the team, and thank you very much for your time, and happy to take the questions. Y las preguntas las puedo coger ahora en español si queréis.
Muchas gracias, Sergio. Bueno, ahora quisiera ceder la palabra. ¿Hay alguna pregunta del público? ¿No?
Una pregunta sobre la interferencia de estrellas. Normalmente para la interferencia necesitas luz coherente, ¿no? ¿Cómo lo haces con telescopios que tienen una distancia entre ellos, o la luz de las estrellas tiene tanta coherencia, o cómo funciona esto?
Buena pregunta. La coherencia entre la estrella, normalmente los sistemas tienen que tener delay lines para corregir eso. Y eso es exactamente lo que se está buscando. Lo que se busca es qué tipo de coherencia hay. Porque esa coherencia entre las estrellas, que la mayoría de las veces no están resueltas, son point sources en el cielo, ese tipo de coherencia lo que te está dando es información acerca del tamaño de la estrella, acerca de si hay una estrella y un planeta. Ese tipo de coherencia es la información exactamente que se busca. Y esa coherencia se relaciona con fases, si hay planetas, si no hay planetas, si una estrella es una rotación, depende del plano en que rote. Hay muchas partes de esa información de coherencia, normalmente coherencia espacial, no temporal, que te da la información para calcular los factores intrínsecos de masa, de rotaciones, etcétera, etcétera. Pero la pregunta es que es complejo. Es complejo porque necesitas tener lo que es el fringe tracking, por lo cual también necesitas tener procesos activos. Como bien dicen entre telescopios, la foto que enseñé antes tiene baselines que tienen delays lines, tienen que estar activamente cambiando para seguir esa correlación.
Ok, gracias.
¿Alguna otra pregunta? ¿No?
Gracias, buenas tardes. Yo quisiera preguntar algo un poco más general con respecto de todas esas, digamos que aberraciones o materia o antimateria. Un instrumento que, bueno, de toda esa materia que pueda haber en el espacio entre un objetivo y otro objetivo, ¿habrá algún tipo de radiación que no esté definido, vamos, o que no sea como un rayo gamma, que también genere algún tipo de dificultad en cuanto a la apreciación de objetos a partir de un satélite o de aquí de la Tierra, para que sea un dolor de cabeza, ¿no? Que genere un problema de esto, o incluso algún fenómeno físico como que si el espacio es curvo y estas cosas.
Sí.
¿Habrá algún instrumento
Sí.
que supere ese tipo de obstáculos? ¿Se ha pensado en cosas de ese tipo?
Sí, sí, sin duda. De hecho, el espacio curvo, hay una cosa que se está estudiando que es el lensing. Se llama básicamente lo que se utiliza ese espacio curvo para inferir propiedades físicas del objeto que estás mirando. Lo que significa, si tú tienes un objeto que está detrás de otro que estás mirando, ese objeto infiere un cambio, una curvatura en la luz que estás observando. Y eso se utiliza también como un sensor para calcular las cosas del objeto. Eso es una de las cosas en el que se llama lensing, ¿vale? Lo otro, lo que has comentado antes, el primer instrumento que hicimos de OH gratings para el background es básicamente para mirar si hay algo más fuera. Lo que se quiere mirar es para intentar llegar al suelo de ruido más básico para mirar lo que se llama el cosmic background, ¿vale? Y esa es la idea de ese instrumento, la motivación de ese instrumento siempre fue esa. Fue decir, vamos a remover todo el background que haya para ver si hay algún tipo de continuo en el que no lo estamos de momento detectando, porque está por encima, está por debajo de todo background y todo lo que vemos. Ese es el otro fenómeno que decía antes, que hay cosas todavía ahí fuera y en eso influye cosas como la materia oscura y otras que son parte de la motivación de ese primer instrumento que se hizo para astrofotónica. Con lo cual hay muchas cosas en el sentido que, por ejemplo, fotónica se podría intentar meter de alguna forma porque hoy en día lo que, de momento, astronomía siempre ha estado gobernada por espectroscopía, por cosas básicas de cogemos la luz, miramos el contexto en longitud de onda y sacamos información. Pero por eso se está moviendo un poco más al tema de sacar más información de esos fotones que vienen. Sacar más información en temas de fase, sacar más información en temas temporal, en temas de polarización. Porque esa información extra que hoy en día se puede sacar con instrumentos más sofisticados es la que te va a dar la clave para esas cosas que no conocemos, ¿vale? Esas cosas, esos fenómenos que no sabemos cómo funcionan. No sabemos si hay luz, si hay más luz en el background. No sabemos si las estrellas, si muchas estrellas tienen polarización circular, si no la tienen, si se conservan, si no. Ese tipo de cosas son las que astrofotónicas en un momento dado, yo creo, en mi opinión, en mi modesta opinión, que en algún día podrá crear instrumentos fotónicos que te pueda dar extra información de esos fotones que llegan, no solo la intensidad y la longitud de onda, que es algo un poco básico, ¿no?
Bueno, muchas gracias. Bueno, creo que se nos ha terminado el tiempo y pues la verdad, solo quisiera agradecerte mucho, Sergio. La verdad fue una plática muy buena. Son muy interesantes todos los temas y han avanzado muchísimo, ¿no? Entonces, muchísimas gracias por tu tiempo, por tu plática. Y bueno, la invitación a venir a México queda sobre la mesa. Cuando gustes, estás invitado. Entonces,
muchísimas gracias a todos.
Gracias.